We're going to continue with signal processing. In particular, we're going to talk about an important application which involves the Fourier domain and is commonly used for almost every type of signal processing, which is the idea of filtering. So filtering is this concept we're going to use, which is going to take the idea that we want to manipulate the Fourier domain, in other words, and for us to clean up signals, process signals, and actually just in general do some operations here in this Fourier domain. Now remember, for filtering, the idea is going to be the following. We're going to have a representation of the signal in terms of the Fourier series here. So right, x of k is going to be expanded in terms of some Fourier coefficients. Here they are. Where each of these a of k's, right, we can determine by taking the signal and projecting it onto these Fourier modes. Now, when you pass through an LTI system, these exponentials that we have here are actually eigenfunctions of the system, and upon passing through, they produce some kind of product here, which is some h, which determines, depending upon the fundamental response, the little h, right? So once you give it an impulse response, that's the little h. So what ends up happening is that response produces an output of how this signal is going to look back in the time domain. So here, this h gives us essentially what happens to every single Fourier component going through our LTI system. Okay, so the system itself, due to its physics or its ever processing that it has, produces an output that's dictated by the fundamental response, which then shows you here how it modifies each of the Fourier components. So you come in with an a of k for each Fourier component. What you come out with is a of k scaled by this component here. Okay. So that's what we're looking at here and this modification. So now one of the things, of course, you might want to think about doing is how do then I, as an engineer, decide to engineer my system so I can get out h of k's that are advantageous for some signal processing application. So that's really what filtering is going to allow us to do, is start to think about the manipulation of those output Fourier coefficients. Okay, so we are coming out with h of k's. How do I modify this? And the way you want to modify this is to think about filtering applications or making bandpass filters. So one of the interesting filter types here is what's called, just a step function, which is I come in with h, and let's make this filter be 1 if the frequencies are less than, the absolute value is less than omega c, and 0 otherwise. So this is basically going to be a notch filter centered around frequency 0. So here's the conception of this picture here. So around this frequency band, everything in here passes through, okay? Everything outside of there is going to get killed off. So if you're too high a frequency, you get killed off, and if you're high on this end, you're killed off. So what this is going to do is allow a band of frequencies that are living right in here to come through this system, be unaffected by this filter, and if all the high frequencies are going to get actually multiplied by 0 and going to be killed off. This is what's known as a low-pass filter. So the low-pass filter keeps a band of frequencies alive and attenuates all others. Typically, this is an idealization right here. This is typically, you can't make filters this clean in terms of just exactly killing off frequencies. And actually, there's also implications of sharply cutting off frequencies as well. Oftentimes what we do is make a low-pass filter, which is a little smoother than this very strong notch filter that we would have. You can make other types of filters. So here are some other types of filters that are based upon the same concept. One is this high-pass filter. When you have high frequencies, you multiply by 1, but all the low frequencies, the opposite of this low-pass filter, all the frequencies near 0 frequency or between omega c and minus omega c are multiplied by 0, which means they're killed off, and then all the high frequencies are passed through. This is called a high-pass filter. So you just delete all of your low frequencies in your signal. You can also do bandpass filters, which is you can select a band of frequencies you want to get through. Here, omega C1 to omega C2, and typically what you do is do both sides so that you can pull out real signals, sines or cosines. So here is the band pass, which is only the frequencies living in a band of frequencies that you select are going to pass through this filter. So this is a common thing that you might want to do. And again, this is all about engineering the response h of I omega. Okay, so your system is producing a response. You might want to engineer it. So you say, I actually just want to pull out certain frequency bands that matter to me. So for instance, when you think about most applications in that we would do signal processing in, so for instance, if you have a cell phone, there's a band of frequencies that you want your cell phones to be responsive to, and all other frequencies you don't care about. So you could put in a bandpass filter into your phone that says, just look at this band of frequencies at this many gigahertz. Those are the frequencies that are, for me, the signals that I need to be paying attention to. So filters are one of the most common parts of signal processing that you would be working with. There's lots of different filter types. You can combine these low pass, high pass, band pass filters into all kinds of configurations here. So for instance, I'm showing you this here where you have a low pass filter, you kill off a band of frequencies, and then you come back up and you let the high frequencies through. So this is sort of a combination of a low pass, high pass. Of course, we've seen the band pass. You can just do one band of frequencies, but you can also do multiple bands of frequencies to let through your system. So these are all the kind of ideas that you could have in filter design. And of course, not only there's a whole class of research and an entire different course, which is all about filter design. How do you produce these filters? How do you design these filters? You don't normally do a step function like this. You would actually do something a little more sophisticated, or maybe quite a bit more sophisticated, so that it has minimal impact on the actual frequencies that are sitting in there. And so you typically would never do a bandpass like this because it actually has some very undesirable properties if we look at the Fourier transform of what happened on the signal. And so you can design very sophisticated filters that have also very nice properties even when you do bandpass filtering. Okay, so let's take an example of this, and I want to show how we're going to do filtering for an image denoising application. So what we're going to do is we're going to read in an image, and I'm going to add noise to that image, and I'm going to use bandpass filtering, specifically a low-pass filter, to try to denoise that image. Okay, so this might be a standard thing you might do in signal processing, which is denoising of a signal. So I have two pieces of code here, MATLAB and Python. So of course here you got all the standard starter beginning things that you need for Python for import. But here's the pieces of code that matter. One is you're going to first read in the image itself. It's called photo.jpg. I'm going to turn it into a grayscale image. So obviously when you bring in a photo, typically it's colored up in the RGB, the red, green, and blue. And so you mix those together to produce your color profile. But here, what we're going to do is just turn it into an RGB cube or back to a grayscale vector. So, okay, this is ABW. It's black and white image now. Okay, and then what we're also going to do with this is once we have that, we're also going to turn this here and take it and add noise to it. So what we're going to do is for every single pixel, we're going to add random noise. Sorry, I apologize for this. This is kind of annoying here, what's going on. Okay. And then what we're going to do is we're going to actually look at this image in the Fourier domain. It's a two-dimensional picture. It's 600 by 800 pixels, which is actually quite small. And what we're going to do is put it into the Fourier domain, and the FFT command is going to actually allow us to do a Fourier transform to give all the Fourier coefficients both in the x direction and the y direction of the pixel. And that's called FFT2. And we can call that directly here in MATLAB or in Python and pull that in. And then the last thing we do is this command called FFT shift. When you actually use a Fourier transform, what it does is it actually takes the image and it shifts it over. This is part of the algorithm that it does. It's called the fast Fourier transform algorithm. It does this butterfly filter, which takes the image and shifts it. And so we have to undo the shift for plotting purposes, and that's what this FFT shift command does. The equivalent of that in MATLAB is given here, and so what you can see here is we read in the image, we turn it into a grayscale, and in MATLAB what we're going to do is going to turn it into double precision number here. So because right now it's in, when it comes in as an image, it's a uint8 format, and then we add noise to it, again FFT to it, so put it in a two-dimensional domain. That's going to put us in the frequency domain where we want to do our filtering, and then shift it, and then we can plot. Okay, so when we plot this, let me just show you this looks like. This is the image. So here's the image without noise. So it's a coffee cup, and I've made this color map pop. Remember, this is a black and white photo. I could plot it in black and white, but I instead decided to do it in this color map hot. So that's the image itself. And if we take its Fourier transform in x and y, this is what it looks like. This is the Fourier transform, and what I've done here is I've actually plotted this. So one way to think about this, along this axis are the frequency components, the k of x's or omega x's, and along here are the omega y's, right? These are our e to the I kx, e to the I ky. So those k's sit along here. So it's like your coefficients, what I'm actually plotting are the a of k's in the x direction, a of k's in the y direction. In other words, how much of this picture show up in these Fourier modes. Okay? And this is what it looks like. And again, I've plotted the log scale, because if I didn't plot the log scale, all you'd see is a bright dot right at the center. So most everything is actually right at the center point, all the information to represent this image here that we're looking at here. This is kind of interesting because what it says also is, if you look at this image, most of it is zero. You know, the coefficients in the Fourier domain, most of it is zero. And in fact, this is the entire concept of compression algorithms, because when you take an image like this and you transform it into this Fourier domain, most of the Fourier coefficients are zero. So you could actually then just prune them out and keep only the non-zero components. And in fact, maybe if you keep about 10% of the information in the Fourier domain, you can still almost perfectly reconstruct the cup, but now you've saved, you know, you're compressing it, and so you're saving only 10% of the information. So we're not going to talk too much about compression, but this here clearly shows that if I keep the image in pixel space, I have to keep all the pixels, but if I use it here in the Fourier domain, I can actually keep only a fraction of the information and recover this image. Okay? So compression technologies sit directly in this concept that we have here. Okay, so let's actually take this image and add noise. So what I did is I actually took this and I added random Gaussian variable to all the pixel space, and so now my image here, it's this coffee cup with a bunch of noise added to it. And if I now Fourier transform it, here's what I get. Okay, so I've really taken down the quality of the image by adding a bunch of noise, but you can see a lot of the noise, it's everywhere, spread out over the entire KX space, but most of the important information is still sitting here. So what we're going to do is we're going to write a filter to just take out the information that sits mostly around this regime here. Okay, so I want to build a little notch filter that's going to look here near the zero frequencies. And we're going to ask the question, if I took that filter and I filtered it out, it's going to cut off all the noise that sits around there. In other words, all this noise that sits in here, and I'm just going to look at most of the signal that's in there, and then inverse Fourier transform it and see if I can denoise this image a little bit. Okay? From this very poor representation now of this cup, which is happening for us. Okay. So here's how I build this low-pass filter. So I'm going to low-pass filter in X and Y. And again, this is just a representation. This is a kind of a sophisticated example to give right away in the beginning of the chapter. However, it does show that this filtering application has a very nice application directly in terms of like even just image cleanup. So here are these filters that I built. All I'm going to do is when I take these filters, I'm going to come up here in this first line. I'm going to basically create a mask, and then in this mask, I'm going to take the middle of the mask is going to be basically zeros everywhere except for that middle region where I'm going to multiply by 1. So that's what this is. First make a bunch of zeros, and then in this middle region where I want to filter, that I want to keep the signal, which is near those zero wave numbers, have a mask of ones of width 50 by 50. So in other words, what I'm going to do is I'm going to look in that little box in the middle, and I'm going to keep a total of, it's 50 frequencies one way, 50, so minus omega c to plus omega c, which is 50 to 50. So there's going to be a total of 101 frequency components that I keep from my Fourier transform. That's what this piece of code does. I write this into my filter, and then all I do is take my filter and I multiply it by the Fourier transform of that image. I then FFT shift it back and I invert the Fourier transform. So that's it. So I'm just taking that image, and you'll see this in a minute. I take the image in the Fourier domain. I took out a little region where I want to keep all the signal. That's ones. Every place else is zeros. And then I multiply that together in the Fourier domain, bring it back. And here's the equivalent code in MATLAB. So in MATLAB, what we're going to do is we're going to take that, again, width of this thing is 50, and we can change this, of course, keep more information, less information. And then I make my initial multiplication by zeros, and in a small region in the middle, I have ones. Those are the frequencies I'm going to keep. So I basically build my filter, multiply by the Fourier transform, FFT shift it, and then inverse Fourier transform it. Okay? So these codes are available for us to look at. And so this is what this code does. I start off here with my noisy image in the Fourier domain, and so most information is here. And of course, I've got noise everywhere in this thing. And so what I want to do now is say, okay, take this and take a small region where most of the information is. And so that's right here. Okay, so take that information. Here it is. And then what I want to do with this is now multiply it by this mask. So it's zero everywhere. So in other words, I zeroed out all the space around it except for this little box where I'm keeping just that. This is my notch filter, my low pass filter that's only keeping those frequencies that you see in that little box. I'm throwing everything else away, multiplying by 0 because mostly it's noise. Okay? So I do that, and now I have my new Fourier transform, which is, this is now what it looks like in the frequency domain because I multiplied everything by 0 except for this little patch. I inverse Fourier transform, and this is what you get. Now this is the recovery of this denoised signal. Of course, it still doesn't look great, but you actually cut off quite a bit of the noise and kind of smoothed it out. There's less high frequency noise in this, and this is now your denoised image. Of course, when you denoise, you don't, we'd love to recover a perfect representation of the cup, but the fact is, you're never almost going to be able to do that when you have noise on a signal. And so here what we're seeing is that what we did is try to take off a lot of the noise, and this is the recovery for that filter once we've taken off all of high frequency noise content. And this is actually an improvement over the noisy image. However, it's still not the best representation. So we can make better filters, and in fact you can change the filter width, the filter type, and in fact you can improve this image a little bit more than this, but really all we wanted to do is really highlight this process right here, which is take an image. If I can manipulate those coefficients, the h, in other words, the h of I omegas, which in this case I did just by multiplication, then you can actually do some of these important signal processing applications, which is denoising of an image. So to finish off where we're going here with filters, filters are going to be one of the most important tools we use in signal processing. There's almost no operation that you would do for signal processing that would not include some kind of filtering operation, right? Filtering is just like a baseline operation where you say, if I'm going to do something for some process that I'm trying to model, almost always I'm going to go look at some dominant frequencies that I need to pull out and work with. And so I need to do some kind of bandpass filtering, pull out the important information that I want to basically manipulate, do my manipulations, and then continue on in the signal processing pipeline. So more on that as we go deeper into the class, but you can see that here we're going to do this directly in the Fourier domain because we have this representation in terms of these hi omegas that we want to manipulate to make some kind of filtering operation.